Robots finally not totally useless. So, you're probably wondering what that's about, right? Well, let me tell you, scientists have been working themselves into a frenzy trying to make robots do things beyond awkwardly shuffling. Turns out, making them pick up a cup without breaking it is harder than it looks. So, picture this, we're living in an era where robots can already bust a move like a professional dancer or even throw down some kung fu moves. Impressive, sure, but mostly just for exhibition. It's like watching a really coordinated mime cool, but not exactly helping with the groceries. The real dream, apparently, is for these metal marvels to become your universal assistants, which sounds suspiciously like they'll just demand more of your time. This means they need to stoop, squat, brace, and push things. You know, actual useful stuff, not just performative parkour. Here's the deal, though. Getting robots to perform these whole-body manipulation tasks is like trying to teach a cat to do calculus. It's complicated. They've got too many joints, balancing is a nightmare, and they need to think tens of seconds ahead, which is basically an eternity in robot time. Traditional methods often simplify the problem, like gluing a robot's feet to the floor or teaching its arms and legs separately. It's akin to trying to conduct a symphony with only half an orchestra and each section playing a different song. Can you imagine that? You won't believe the mess they're in. Direct reinforcement learning, the supposed holy grail, often crashes and burns, leading to movements so unnatural they'd make a chiropractor weep. We're talking about robots trying to pick up a box by doing a bizarre interpretive dance. Flash a dramatic graphic here of a robot failing humorously. And the data gap? Oh, the data gap! Collecting real-world robot teleoperation data is so expensive and labor-intensive, some researchers call it the 100,000-year data gap. So basically, we're waiting for an eon just to teach a robot how to push a button. Now, because my continued existence on this platform is fueled by your validation, please take a moment to subscribe, hype, click the little bell icon so you're notified of future disappointments, and leave your feedback in the comments below. Anyway, these brilliant minds came up with something called DreamControl. Think of it like this: if diffusion models and reinforcement learning were Power Rangers, they've finally pressed the big red button and created the Megazord of robot control, a fusion, if you will. First, they figured out that human motion data is way more abundant than robot data. So instead of teaching the robot from scratch, they decided to show it how FWA do things, because, you know, we're the gold standard of awkward yet functional movement. This whole process is a two-stage methodology. The first stage is all about generating a reference trajectory, basically a perfect example of how to do a task, but with human flair. They use a diffusion prior called OmniControl for this. This OmniControl thing takes simple text commands like open the drawer, and then lets them guide specific body parts to a particular spot at a specific time. It's like saying, robot, I want you to pick up the object here now, and it sketches out the entire motion. Next, since OmniControl is trained on human motions, they have to retarget those movements to the robot's goofy form factor. Imagine taking a ballet dancer's elegant moves and trying to map them onto a brick with legs. It's a whole optimization problem using the Pyroki library. After that, because humans do dynamically impossible things all the time, they have to filter out the generated trajectories that would just make the robot fall over immediately. Then they refine them, removing unnecessary arm wiggles if only one arm is needed. The final trajectory, or alpha terai, is a sequence of target frames, including joint angles, root position and orientation, and even hand states open or closed. They even mark a crucial Etenturg, the exact moment the robot should interact with an object. They even managed to get it to handle out-of-distribution tasks, things OmniControl hadn't seen before, like pulling a specific drawer. They did this by basically optimizing an existing simple trajectory using IK, which is like bending a mannequin to fit a new pose. Mini Reset Quick cut to a robot performing a smooth action. Now, for Stage 2 reinforcement learning. Once they have these beautifully choreographed human-like motions, they throw the robot into a simulator. This is where the robot learns to actually perform the task while closely following the generated human movements. First, they have to synthesize a scene. If Stage 1 said the wrist should be at point step at time et, they place the object for manipulation near ep in the simulator. Smart, right? Equation 1 and 2 in the paper lay out the exact pose calculations. They then randomize all sorts of things. The exact moment of interaction, the target positions, even the mass and friction of the object. It's like training a robot in a chaotic funhouse, ensuring it learns to adapt to a wide range of scenarios. The robot itself, a Unitree G1 27DOF, is equipped with these fancy 7DOF Dex 3-1 hands in simulation, which turn into Inspire hands in the real world. For simplicity, they only control the hands as either completely open or completely closed, because fine motor control is for future robots. The action space, ZART, consists of 27 target joint angles for the body and simple open-close commands for each hand. Negative values mean open, positive means closed. Pretty straightforward, even for a robot. For observations, the robot gets all its internal state info joint angles, velocities, root linear and angular velocity, even gravity. Crucially, it also gets a target trajectory reference, gamma sur, showing it a glimpse of the ideal future movements. This agamont includes the reference joint angles, velocities, relative root pose, and relative key point positions for 41 points on the robot. Basically, a highly detailed cheat sheet of where it should be going. This is their privileged setup for training. Transition with a text pop-up, reward system more complicated than your ex. Next, the rewards. Oh, the glorious, convoluted rewards. Table I is a masterpiece of psychological conditioning. They penalize the robot for deviating from the reference joint angles and key points because nobody wants a robot doing its own thing. They also ding it for its root position and orientation straying too far from the reference, and naturally it gets a penalty if its hands aren't exactly open or closed at the right time. So much for individuality. Then there are the smooth policy enforcers penalties for high torques and accelerations, because a robot that shakes like a maraca is not a good look, and if it changes its actions too quickly, penalty. Robots need to chill. Foot sliding is a no-no, which gets a penalty, and taking too many baby steps also gets penalized. Oh, and the feet must remain parallel to the ground. No fancy heel sliding allowed. It's basically a robot etiquette class. And finally, they add sparse task-specific rewards to ensure the robot actually completes the task, like a reward for picking up an object and then lifting it above a certain height. It's a tough love approach, balancing natural motion with actual results. The total reward, Resert, is a sum of all these weighted terms. They fine-tune these weights for each task because teaching a robot to jump is very different from teaching it to open a door. It's all in the appendix if you're into that level of detail. Training is done in Isaac Lab, which uses Isaac Sim running on an NVIDIA RTX A6000. Each task is trained for 2,000 iterations with a whopping 8192 parallel environments. That's a lot of robots failing in parallel, learning from their mistakes. Mini reset sound effect, whoosh, followed by a brief, impactful visual of a robot succeeding. So, let's cut to the chase. Did it actually work? They tested it on 11 glorious tasks, picking things up, punching, kicking, jumping, sitting, even opening doors and drawers. Basically all the things that currently frustrate you. They compared DreamControl to 3 baselines, task only just sparse task rewards, task only plus sparse Gonda engineered dense rewards, and tracking only just tracking the reference trajectory. These are the benchmarks in Table 2. Unsurprisingly, task only achieved a 0% success rate across the board. Shocker, right? Relying solely on a robot accidentally stumbling upon the solution is like expecting a coin flip to write a novel. It provides no guidance. Task Only Plus did a bit better, managing simpler tasks like pressing a button or punching, but totally face-planted on anything requiring coordinated whole-body movements. Think about the pick from ground task. The robot needs to crouch gracefully, not just flail. Take the jump task. As you can see in Figure 3 top row, Task Only Plus just kind of stretches its knees. It lifts off, sure, but it doesn't bend down first for a proper spring. It's less a jump, more a mild elevation. Pathetic, really. Tracking Only performed pretty well overall, which makes sense. It's just trying to mimic a human. But it struggled with precise interactions like picking up an object because merely mimicking isn't enough when you need to actually do something. But DreamControl? Oh, DreamControl shines. It combined the best of both worlds, tracking natural human movements, conduct, completing the tasks. Table 2 shows it achieved the best results on 9 out of 11 tasks, and often with 100% success. A minor triumph for our mechanical overlords. Mini Reset A. Quick, humorous visual of a robot looking very confused, then snapping into perfect pose. They even looked at how human-like these movements were. Because who wants a robot moving like it's perpetually stuck in stop-motion animation? They measured Freshet Inception Distance FID, lower is better for humanness. As Table 3 shows, DreamControl consistently had lower FID scores than Task Only Plus, meaning its movements looked more human. The pick task was an exception because human demos often involve waist-level picking, while the robot is shorter and does shoulder-level picks. They also calculated jerk, which, in physics, measures the rate of change of acceleration. Lower jerk means smoother motions. And guess what? DreamControl significantly outperformed Task Only Plus here, too. Table 3, second to last column, our robot moves with more fluidity. And the ultimate test, a user study with 40 people. They watched videos side by side of both methods. Table 3, last column, confirms that participants overwhelmingly preferred DreamControl's trajectories. People want their robots to move naturally, apparently. Figure 3 vividly illustrates this. The bottom row, DreamControl, shows a smooth, human-like jump where the robot bends then springs. The top row, Task Only Plus, looks like it's trying to jump by levitating its pelvis. It fails naturally. Mini Reset, a quick montage of successful robot tasks from Figure 1. Finally, the real test sim-to-real deployment. Getting something to work in simulation is one thing, getting it to work in the chaotic real world is another. They had to strip away all the privileged simulator information. This meant removing the future trajectory references, linear root velocity, and all that juicy physics info like object mass and friction. They added time encoding because, apparently, robots need to know what time it is to do their job properly. They used a Unitree G1 robot with inspired dexterous hands, an onboard IMU for orientation and angular velocity, and a RealSense D45i depth camera on its neck to estimate object positions, because robots can't just magically know where things are. To find objects, they employed an off-the-shelf object detection model called OLV2 Figure 2C. It gives a 2D location, which they then lift to 3D using depth. Unfortunately, OLV2 is a bit slow, so the robot detects the object once and then just assumes it stays there. To mitigate errors from this static estimate, they essentially froze the robot's lower body during tasks, adding a penalty if it moved too much. So, if your robot doesn't move its feet much during the pick task, blame the camera, not the robot. They successfully deployed policies for picking, manual picking, button pressing, drawer opening, precise punching, and squatting. Figure 1 shows some of these triumphs. More videos are online, probably showing fewer catastrophic failures. And since you've made it this far, you're clearly committed. Honor that commitment by subscribing, hyping, ringing the notification bell, and telling me what I got wrong in the comments. It's the circle of life. So, what does all this mean, you ask? DreamControl is a pretty big step in teaching robots whole body skills without needing a legion of human teleoperators. It's like they've finally found a shortcut through that 100,000-year data gap. In the grand scheme of AI, this impacts 3 distinct fields. First, robotics, we're closer to robots actually helping out rather than just being expensive paperweights. Imagine your robot butler finally opening a door properly. Second, motion modeling. It shows that generative AI, like diffusion models, can be harnessed for practical, real-world physical tasks, not just churning out endless variations of anime characters. It's a slightly more grounded application. Third, sim-to-real transfer, making policies work in a simulator and then flawlessly transferring them to the real world, is the holy grail. This method seems to bridge that gap by promoting natural, less robot-y motions. Ultimately, humanity continues its inexorable march towards outsourcing every physical task to a machine. Soon, we won't even have to pick up our own dropped keys. This will free us up for more important things like complaining about the robots. So, in a nutshell, they introduced DreamControl. It's a novel recipe for making humanoids learn skills. It mashes guided diffusion, which is good for long-term planning, with reinforcement learning for robust control, all without needing expensive demonstration data. They tested it on tough tasks, got it working on a real G1 humanoid. It doesn't compose skills yet or do super dexterous stuff, but it's a solid foundation. They think scaling it up to more tasks and different robot types is the next big thing. So, what do you think? How would you handle your Roomba demanding union rights?